The JVM is like this enormous toy chest, right? It is like filled with all these libraries, and as simply as discovering that one of them exists, we can take it out, we can play around with it interactively. There's no foreign function interface, there's no need for us to enumerate everything before we can use it. But once we start to do this, it becomes clear that Clojure and Java don't see eye to eye on everything. A lot of this derives from the fact that Java has mutable state, and that the objects tend to be this combination of data, things that act on that data, and the actions that that data describes. And they're all just kind of mixed together. And there's also a lot of incidental complexity, and this derives largely from what Java doesn't have. It doesn't have first-class functions, it doesn't have closures, it doesn't have a simple way to describe data, and so you end up getting code which is a very indirect expression of what it's trying to do. And so we're here to talk about distilling Java libraries, and distilling is reducing something to its essence. And that doesn't mean that we're going to hide the Java away. A lot of people who get enamored of Clojure have this very strong negative aesthetic reaction to seeing the camel case mixed in with everything else, and they want to just put it in some deep, dark recess of their code base and pretend it's not there. And I'm not going to say that that's wrong, but it's not useful. And that's not really what we're going to discuss here. What we're going to discuss is making the structure of the code reflect what we're trying to do with it, having everything be aligned with our intent. And I don't mean the intent of the library as it was written, but rather how you intend to use it. And consider if you have a Swiss Army knife and all you need is a bottle opener, the ceremony around getting to that bottle opener doesn't help you, right? This, in other circumstances, this would be a useful tool, but for you, this is just an overly complex bottle opener. And so, at the same time, we need to consider that we're not carving away code. We are adding code to change how we're interacting with it. And that's a choice that you need to make sure is the right choice. Again, we do not need to enumerate things to be able to use it. We can just use a Java library. Sometimes that is just the right thing to do. And so the reasons that you want to do this, the reasons that you should add code, is if you feel that there's a lot of incidental complexity, that you don't need all the features, or that you're trying to create something which is a gestalt, something which is more than the sum of its parts. You're trying to bring a bunch of disparate libraries together and turn them into a coherent whole. And while going in, you should have an idea of what it is that you're trying to accomplish, what your intent is with respect to this code that you're trying to interact with. That's a process. You're not going to be able to reason from first principles about this. A lot of your assumptions and preconceptions are not going to survive first contact with implementation. And so you're going to try something, and you're going to find out where it doesn't work, and you're going to feed that back in. And as time goes on, you need to be aware of what the assumptions you made were, or what the assumptions were when you wrote your first line of code. And you're going to need to constantly keep in mind whether or not that's still valid, whether that's still something that you believe to be true. And sometimes this means tearing down code that you've already written, but that's what this is. This is an attempt to hone in on really what you want with respect to this library, what you want to accomplish. And this is worth getting right. The code that we write is how we describe what we do elsewhere. And Mark Twain has this great quote, which is saying that the difference between the right word and the almost right word is the difference between lightning and a lightning bug. And I think we're here because Clojure gives us these moments of clarity, right? Not all the time, but this is something that we should always try for, like really reach for. And with the sort of motivational abstract that's out of the way, I'm going to just dive into code. I'm using Java 2D as an example here, not because Java 2D is representative of all Java libraries, but because it has some properties that are good to think about. One is that it has unavoidable side effects. If we're drawing something, we have to have a side effect. We can't reduce this down to something which is pure and functional, or not completely. Also, it's a well-designed library. This is not sort of a straw man. I'm not trying to show you how to get rid of factory factors or anything like this. That's useful, but I mean, frankly, you can figure that out on your own. We're talking about the inherent complexity of having Clojure and Java work well together. And finally, I get to show you pictures, so hopefully I can hold everybody's attention. All this code is already up on GitHub. It's under Z Tellman. The project is called Scrawl. You don't need to look at it, but there's going to be a lot of code that I go through here. You may not necessarily have your head wrapped around all of it before I move on to the next slide. That's okay. It's all there for perusal. It can be, ran at the REPL and everything like that. And if you have any questions afterwards, we can chat. So here's how you draw a triangle. You take a graphics object, and the graphics object in Java 2D is sort of your portal to the world. It's how you make things appear on the screen. It's how you describe how those shapes will look, how they'll be altered. Everything flows through the graphics object. And so with this graphics object, we call fill polygon. We give it 3 vertices, and it draws an equilateral triangle. And to get a graphics object, we create a JPanel. We override its paint callback, and the paint callback is passed a graphics object, and we use that to draw the triangle. And we get this, which is an upside-down half of a black triangle in the upper left-hand corner. And it's actually only 2 pixels tall, so I made it larger so it's actually obvious that it's there. This is not what we want. And the reason that we have this is because the origin, 0, 0, is conceptually in the upper left-hand corner. Because the positive y-axis points downwards, we're going from the upper left-hand corner to the lower right. And because we only created something which is 2 units tall, and a unit equals a pixel. So let's fix this. First, we call translate on the graphics object. And translate tells the graphics object, everything that I tell you is actually shifted over by this much and down by this much. In this case, half the width and half the height. Then we scale the graphics object. And this says, everything that I tell you, it's not a pixel. It's actually 200 pixels. And the y values I'm giving you are actually negative, so that we can actually get things to look right side up. And then finally, we set the color to red. And the graphics object is stateful, right? We tell it the color, and that applies to every subsequent thing that we ever draw until we change the color again. And then we call draw triangle, and we get this. So success, right? We have a big red triangle in the middle of the screen. Let's try to clean this up a bit. First, we define a callback, and we create it as an atom. And the reason for this is that we don't want to necessarily draw one thing and then have to close the window and reinstantiate the window and everything like this. We want to be able to update this, primarily because we're at the REPL, but potentially also within an application. And you can do this by just redefining vars if you want to. But this is actually a little bit fraught with peril, because if you ever close over a var, if you ever pass in the var, and then it just becomes a value, updating the var won't change anything. And there are ways around this, and Chaz actually alluded to this in his talk, but I find it's a lot easier and just easier to reason about if I make it very explicit, right? This is a thing which holds a value that can be changed. And then, because the graphics object is involved in everything we do, and because the graphics object is only valid within the context of this callback, it's a pretty easy win to have this as a thread local binding. And so we create a dynamic var, which is earmuff graphics, and we type int it. And then we create a new paint callback. We do all the transforms that I discussed earlier. And then we look to see if there's a callback. If so, we bind the graphics object. And then we call our callback. And with a minor modification to our draw triangle function, which is turning into something that takes no arguments and uses earmuff graphics, we get the same red triangle. So no changes, just refactoring. We're now starting to kind of build away from doing just Java enclosure. So let's do something new. We'll define a map of colors, of keyword descriptions of colors onto the Java representation. Okay? And recall that color is stateful here. Like, ideally, for us, what we want is every single time that we draw something, we pass in the parameter of the color that we want to use there, because then we could just use another thread local binding. But this is not useful for Java, right? This is a Java API. It's designed to be convenient in that context. But there's a problem, which is that if we call into a function and it draws something and it sets the color to something new, that bleeds out into everything else, right? We want this to be scoped. And we don't want this to be scoped by convention like it would have to be in Java. And so we need to emulate this thread local behavior. We want to emulate the sort of scope that we would have here. And so to do this, we write a macro. And first, we get the current color on the graphics object. Then we set it to whatever our new color is. We evaluate the body. And then within the finally clause, we set it back to whatever it was. And this try finally structure is because if an exception is thrown, we're still going to set it back to whatever it is. This is a really common thing that you'll see within a lot of macros. You typically want to make sure that you do something and then you definitely undo it. So we can do this. We can now draw a blue triangle. We're really going places. So let's look at transforms. Okay, we have a big red triangle, and when we scale, we are shrinking not the triangle, but rather the frame of reference for the triangle, right? If we draw a triangle which is a unit triangle, it's going to be smaller, but that's sort of outside of the triangle's frame of reference. It still thinks it's the same size. It still thinks that it's at the center of the world. And so if we rotate it, it will rotate. If we then translate it up, it translates in its up direction, right? And then when we finally rotate it 180 degrees, it rotates around its center axis. And so this is actually an even more sort of intractable problem than the color, because in order to make sure that we're not bleeding out these transforms into the rest of our calls, we need to do the exact inverse transformation in the exact reverse order, because it actually matters how we evaluate this. And so this is a big mess. And so we do the same thing. We get the transform, we evaluate our body, and then we set it back to whatever it was before we evaluated the body. And some of you may be realizing that there's a pretty strong structural similarity between these two macros. And your sort of wheels start spinning and you're thinking, I'm going to write an macro. I'm going to write the macro that expresses both of these macros. And I can't tell you what to do, but don't. I mean, there are cases where this is a valid thing to do, but for the most part, this is a lot more trouble than it's worth. And if you've never tried to nest syntax quotes, you should. It's an experience in frustration, but you should try it. And someone here is going to prove me wrong and is going to give me a pull, request on my thing and say, look, it's easy, it's done, and that's fine. But this is typically more trouble than it's worth, and this is like really just one of those obvious bits of yak shaving that Clojure lends itself to. And really, frankly, if you're starting to write macros that write macros, this speaks to a certain potential problem in how you're approaching your implementation. And so that is a code smell. So what we're going to try to do here is draw the Sierpinski triangle, which is a really simple 2D fractal. This is sort of the graphical equivalent of the Fibonacci, and you should take it as equally trivial, but this is something that I can cover sort of beginning to end in the scope of this talk. So the way you draw the Sierpinski triangle is you take a triangle, you shrink it down to half its size, and you draw it twice more. And then you take that, and you shrink it down to half its size, and you draw it again, and over and over and over again. And so we can do this. We can write a macro. We can take the body and we put it into a function. And the reason that we're not expanding this out in place is that we're going to actually execute the same code 3 times. And typically, if you can, you shouldn't be just expanding out multiples of the same code. The JVM can get a little bit cranky if you have really, really big macros. And then we do a with scope transforms and we shrink everything down to half its size. And then we draw it 3 times by translating it to 3 different positions. And we can nest this. We can actually do multiple transformations on this triangle and get multiple iterations of this fractal. And we can even, if we're feeling really clever, write a macro that expands out n many of these nested Sierpinski transforms. And so we can do this. And we succeeded. And this works. And it actually is good in a couple of ways. One is that it does, in fact, work, and it was very simple to get here. And we're actually very close to the Java 2D API. This is like just a couple of conceptual leaps away from that. And what that means is that we can rely on the tutorials for the Java 2D API. We can rely even on the Java doc for the Java 2D API. And let me tell you, you're not going to get documentation as good as JavaDoc for free in Clojure. You actually have to work pretty hard on it. Even if it's just type information about all these calls, that's a lot better than your one-night effort to explain how everything fits together. And people are going to have to be looking at your code, and it's going to be kind of a less than ideal situation for everybody. But unfortunately, there are also some problems. It's completely imperative, right? There's absolutely no separation from saying what we want to happen and it just happening. And this cuts Clojure off at the knees, right? We are good. We work with data. We can transform data. We can filter data. We can we can do all these sorts of things, and there is no data here. There's just stuff happening. And we're using macros to do complex stuff, which means that we have effectively said every further higher level operation that we need to do also is a macro, right? In order to compose a bunch of these transforms together, we wrote another macro. And so if you're at the top level of abstraction in your program, this is okay. But if you're going to consume this and want to use this elsewhere, this is a real problem. So let's try a very simple change here. Let's say that our draw triangle function is actually a triangle renderer. And now we have a render function which just invokes the renderer. And this may seem kind of silly and pointless, but consider that now what we can do is we can take a function, have a color, and return a function which draws the same thing, but now it's a different color. And we can take a function which draws something, and we can return a function which draws it somewhere else. Okay? So what this means is that now we're dealing with something here, something which represents something that we want to do. This is something that we can act on using Clojure's, strength, right? We're all of a sudden bringing it back into our wheelhouse. And so now, to draw the Sierpinski triangle, we define a series of offsets. We define a function which, given a set of offsets, returns a function which is translated and scaled appropriately. Then we map that over our function 3 times, and we return a function which invokes this 3 times, or these 3 different versions of it. And so now what we can do is this, is we can define an infinite sequence of Sierpinski transforms, right? We're starting with the base case, and then we have a function which is iteratively applied each time. And so now, if we want to render this, instead of having to nest all these transforms together, we just index into it. We render the nth element of this infinite sequence of this fractal. And so, again, this is a very tiny little sort of subtle transform, but the fact is that what we did is we turn actions into data. It's a limited form of data. It's a function. It's not really very rich or anything like this, but it's still something that we can pass around, something that we can act on. And so this is a lot better. This is a significant improvement. And it's more idiomatic, and it lets us actually use some of Clojure's operators. And other code can operate on this more easily, right? And so we can actually use this as something that other people can consume. Unfortunately, we don't know what any of these functions do, right? We have a function. We can transform it. We can move it. We can change its color. But we can't actually look at what it will do unless we just draw it. And if we're trying to test this, this puts us in a bit of a problem because the only way that we can do this is have a bitmap that we compare to or something like this, right? And this is not really acceptable for most real-world cases. So what we want to do is we want to have this thing not just be data in the sense that we can pass it around, but be data in the sense that we can introspect on it, data in the sense that it is visible. And so we're going to define a protocol. And I will note that for this case, a protocol is complete overkill, right? We're just drawing triangles. We could do something simpler. But consider that we may want to draw text. We may want to draw circles, right? We may want to do these other things which have these same properties and won't be accomplished in the same way. And so I'm trying to, at least indicate a direction where this would be a less trivial example, and that's why I'm using this. So when we create a polygon which implements, or rather satisfies this protocol, we're lucky. Java 2D gives us a polygon object. We're cheating, right? And the reason I didn't use this from the get-go is because most tutorials about Java 2D don't do this. They show you how to just draw something. Why have this layer of indirection, right? This seems almost like complete incidental complexity. It's over-engineering. But it's not. This is actually something which is genuinely useful, and this is how we're going to get to something which is really an idiomatic solution. And it took us all of 10 minutes to get from one to the other, and so this is not exactly like a long struggle for enlightenment, but consider that your initial sort of perception of what the library is and what the valuable parts are may not stay the same, right? Things that you dismiss out of hand as over-engineering may end up being the very thing that makes it really a useful library. And so, again, question your own first impressions about this, right? Go back with sort of fresh eyes and look at the Java doc or whatever else to make sure that you really understand how it can be used from Clojure. So, again, we have the polygon object. Java 2D does all the heavy lifting. For rendering, we do the with color. We fill the graphics object with this polygon, and that's very, very simple. Transform is a little bit more interesting. What we're doing here is that this is completely immutable, right? This is functional. We are taking a transformation, a description of something that we want to do to transform this. We are creating a transform shape using something called an affine transform, which is, again, something that Java 2D just gives to us. And we're returning a new shape. And so this looks very familiar, right? To create a triangle, we have a default color, but otherwise we're just creating a polygon which has these same vertices. And this returns something which is a record with the keys polygon and color. And we can actually look at what's in that polygon. And if we wanted to sort of build this out a little bit more, we could create a nice API to look at what's in that polygon. But, I mean, again, it's just Java. We can look at it. We don't need to necessarily hide that away. So, when we define a transform, we just take a simple identity. And it's just a Java object, right? And what this returns is a Java object. We're not trying to hide this away. We're not trying to put this in a map or have some sort of wrapper for this. All of our functions are Clojure, but our objects are completely just vanilla. And so, unfortunately, affine transforms aren't immutable. When you change them in place. So to work around this, we need to create a copy of this. And so we create a brand new transformation, which is a copy of the other thing. And then we update it using, in this case, a scale instance, right? And concatenating is basically a composing of these transforms, a multiplication. And then we return it. But consider that in terms of the actual meat of what we're trying to do, the only really meaningful part of that was the scale instance. Everything else is just sort of structural to get around the fact that we want this to be an immutable transformation. And so what we do is we create a macro. And in this case, what we want to do is we want to capture the structural aspects of this. And we want to make it so that all we're focusing on is the really meaningful piece of it. And what we're doing here is we're creating a defen macro. And I want to just note for the record, I'm way oversimplifying this. The defen form is actually one of the more complex ones in Clojure. It takes always a defen, always a name. Then optionally it has a docstring. It has an options map. It can be multiple arities, so it's not necessarily an arg list. Like if you were trying to create a really robust defen macro, you got to work at it. And if you're trying to expose this macro to other people for them to use, then you need to really be sure that this is a completely drop-in thing that can accept all the forms, all the structures that the defen macro can. But if you're just writing it for yourself, it doesn't really matter, right? I mean, you know how you're going to use it. And so what we're going to do here is we're going to really just simplify this. We're going to say that it takes names, it takes args, and it has a thing in the body. And as long as we use it the way that we plan to use it, that doesn't really matter. So first what we do is we take the original transform. And what we do is we actually take the first argument from the arg list, and we just put it there. And again, we're making some real assumptions here about how this function is going to be called. Then we create the copy, just like before. Then we concatenate it, just like before. And then return this new transformation. And so this code that we wrote before is now just a body that says, here's what it's going to be transformed with, right? We've distilled this down to just the thing that's meaningful about this. And so if we create a rotation or a translation, then we can do the same thing, right? It's a very concise expression of what it is. And I want to point out that nowhere do the x and y parameters, those are completely irrelevant to the macro structure there, right? It's just matching up. It's putting the arguments here. It's being used in the generation of the scale instance. It doesn't matter if we know that this is going to be it. You can have an arbitrary set of arguments here. All we're doing is just kind of putting the pieces in place. And this is effectively just using the macro as a template, but that is really most use cases, right? And so that's okay. So again, we define some offsets, but now we can do something even more interesting. We can define the transforms, the three transforms, which are shrinking it down and moving it over to the appropriate place, that we're doing over and over and over again. These are data 2 now. And so in this case, we take the offsets, we map over them, we take a transformation, we scale it down, we translate it. And now this is just stored for our usage and potentially our introspection anytime that we want it. And now our Sierpinski transform is actually something which takes a list of shapes and it does the same transforms over them, and it returns a list of shapes which is 3 times longer. And that's all we need. All we need to do now is to create the same infinite sequence, define something that is called render all, which takes a list of shapes and draws them all, and draw our Sierpinski. And this is where we're going to stop in terms of trying to improve this, because this is, for this very trivial use case, good enough, right? We have the ability to look at all the data, look at all the things that we're using to affect change, all the things that we are using to do side effects. We have decoupled these things from each other. And we're able to use all of Clojure's tools now, right? Not only can we do, map operations over these functions, we can look at them, we can filter them, we can do all the various things that Clojure is good at. There are some problems. One is that being able to redefine the context in which something is being rendered means that we only need one of them. And we can just do an operation many times. And so if we're actually creating one object for every tiny little triangle in here, this may not actually be very good. We're going to run out of memory at some point. And so to fix this, we basically need a hybrid approach where we would take a certain amount of these shapes, or whatever a meaningful subset of these shapes are, which may just be 3 triangles or a triangle or something like that. And then we can use the same macros, the same composed functions that we were using in the earlier steps. And, that's okay. That's very reasonable. The other issue is that this no longer resembles Java 2D. I mean, you still have some of the same objects underneath the covers, but you're going to have to write documentation now. And it's going to have to be good, and your examples are going to have to be, things that you think through. And furthermore, while we have something which works very well for drawing triangles, it's not clear that this is going to work well for text or for any of the other things that Java 2D can do. And if all of a sudden you're like, oh, wait, my scope is a little bit broader than I thought it was, all of the things that you did, all of the stuff that you threw out, all the simplifications that you made to how we're interacting with this may no longer be valid. And so you need to again, this is why it's important to understand what you're trying to accomplish, because changing what you're trying to accomplish invalidates everything, potentially. And so I'm not going to necessarily look at how this deals with text. This is sort of outside the scope of what I'm trying to talk about, but I do want to just say that, this is a very trivial example. And I've said this multiple times because I don't want to make this seem like I'm trying to say this is what Java is. Java is a bunch of triangles. Java is just something which, is doing side effects and has this sort of stateful, central, like, God object and like all this other sort of stuff. These are not universal facts, and the point is that nothing I could say here, no example I can come up with really encompasses the issues that you're going to find. And so what I want to focus on instead are the questions we were asking each step of the way, and understanding whether it was good enough, understanding whether we really wanted to move on, or they wanted to try to engineer out a better solution or a more complex solution. And I got through this a lot faster than I intended to. I want to just kind of say that, the meta questions, the things that drove us to trying to get a much more complex solution at each step of the way is the lesson, is the thing that I'm trying to talk about. And I try to distill this down to sort of maxims or something that, rises above the level of practical application. I couldn't. So this is what's there, but, please don't fixate on the details. Fixate on the thought process that's behind it. And so with that, I'm opening up the floor to questions. You get out early.
Do you think, though, that even though this example was trivial, do you think that the steps you went through are a good way to approach other APIs?
That's my hope. Yeah. So, in general, you start with writing idiomatic Java with Clojure, right? You take whatever tutorial you can find, whatever is out there, and you make something that works. Like, you have proof positive that you're doing it right. And then you start to kind of peel away the bits that hurt the most, right? And the question, how we did this is not necessarily there, but that is a good universal recipe for approaching these sorts of things, right? Make sure that you understand the API, that you can make it do things, and then start to think about how you'd like to make it better. And again, this is kind of so general as to be almost empty, but yes, that is, I think, a good model for this. Yes?
Are there any Clojure projects that you particularly think have done a really good job of this kind of stuff?
Seesaw is excellent. Dave is doing he's doing excellent work there. And, Swing is a exemplary project for its kind in that it's really, really painful and is really inconsistent and has all these sorts of things which, if only they're a little bit different, would be so much less painful. And so to sand away all these rough edges, it really does a really excellent job of this, right? And more to the point, what he does is he doesn't hide away the Java objects behind something else, which means that he doesn't sort of put you in a padded room and say, here are the things that you're allowed to do because this is what I've built out as, your capabilities. He's leaving all of the things that Swing allows you to do at your disposal. I've written some libraries which don't do that because I couldn't figure out a good way to express this idiomatically and still, leave all the bells and whistles on. And I might, if I were, thinking sort of glass half empty about it, that is a failure because that is something that you should shoot for, right? You should never cut off avenues because you couldn't think of how to fit them in your perfect view of the world. Yes?
At the risk of shaving the yak here, the steps that you went through to try and make it more idiomatic towards the more idiomatic closure towards the end, you were creating all these at-run transforms, which weren't really necessary until you actually go to render. So
yes,
there could be a more closure of simple.
Well, I may have glossed over this part a little bit, but there are two ways you can represent a transform. One is, this is the global, everything I draw is this transform, and the other is, I have data, they have vertices, I can transform these in place, right? I can do this outside of the context of when I'm drawing stuff. And that's what that affords you, right? This is now, we're just dealing with data, there's no context in which this is valid, we're referentially sort of, transparent here.
So my point is that you're holding on to all of that Java object, that entire Java object allocation.
Yes.
When perhaps you don't need to.
No, and as I pointed out, right, this is not the most memory efficient sort of thing, and maybe you do some sort of hybrid approach, which, is the sort of more powerful thing. We're going from one end of the spectrum to the other, and the sweet spot doesn't always lie at the far right. And so, I'm trying to look at how this works, and I think that in a lot of cases where you're not creating a lot of objects, making things more dataful is the best option up until the point where you start hitting at sort of limitations of the environment that you're running in. Yes?
I'm interested in things like Seesaw and Quill and sort of doing graphics closure generally. And I wonder if you care to speculate, is there an impedance mismatch between closure and the way the graphics are generally done, period, because of the OpenGL state machine?
No. Okay, so, full disclosure, my first project in Clojure was an OpenGL library, right? And I wrote it, and it was kind of cool and could do some cool stuff, and was ultimately sort of a failure because OpenGL is an enormous API, and I couldn't expose it all. And so that's kind of sitting there. It allows you to do some cool stuff, but it didn't supplant what it was trying to close off from the world. And so as you look at how this is implemented, this standard sort of state machine, and like you see this in Canvas, you see this everywhere. Like this is just how 2D graphics and to a certain extent 3D graphics are done. Yeah, there's a little bit of an impedance mismatch there. However, when you look at how things are actually being done in modern OpenGL, what you have is you have a bunch of data. The programmable pipeline, right? And I mean, this is like totally off the rails here, but like, you guys are along for the ride. You have a bunch of data which represents vertices and textures and all this other sort of stuff. And then you have a program which is written in shader language. And you put in the data, and out comes the other data, right? And there might be some stateful stuff in this black box, but these are pure functions, right? And the way that modern graphics engines deal with this they compose a whole ton of these things together. And it's really painful to do in C, and it's really easy to do in Clojure. And like, I was just kind of at the cusp of like, there's some cool things. Like I created something which does like computational fluidic dynamics, like just simple sort of Navier-Stokes stuff. And it composed together 15 transforms to do it. And it was really, really small code. And you guys, the project is called Penumbra, and like it's got some cool stuff in there, and like there's a lot of potential for this. And I mean, really, more generally, if you look at sort of the trend towards like just coprocessors as this thing that are starting to build up, they're going to be on some level pure functions that you can orchestrate and use together and try to map the interactions between them. And I think Clojure is awesome at that. And there are some gnarly implementation details, and it's not like everything is going to be clean and functional at every level. But if you sort of separate things appropriately, I think that this becomes a really powerful tool. So no, I don't think that that's the case, though everything's in the implementation, and I haven't gotten it right. And maybe someone else will, or I'll take another stab, or whatever. Yes?
Have you seen, outside of the graphics domain, other examples of Clojure libraries that you think are sort of exemplary Java integration?
So, I mean, okay, like they're kind of two things, and the reason I'm focusing on side effects here is that you can't reduce it down to a simple function, right? And then at that point it becomes sort of an API design, sort of a DSL design question, and I think that there are good examples of that. I mean, good examples of these sort of API, everything is a pure function. Chris Granger has done a lot of stuff in terms of like marking out SQL and kind of going over JDBC and all that sort of stuff. And it's well thought out. It has nice orthogonal pieces, but it's such a different sort of question almost. And like that is something that Clojure maps onto a lot more cleanly. So I wanted to do something that I felt was a little bit more, ungainly kind of. And yes, there are some, but at the end of the day, your program has to have side effects, right? And so, at some point, you're going to be interacting with something that does something. And even, web servers, to the extent that they can be modeled as pure functions, that's not always true. And there are sort of, all these sorts of caveats and everything like that. So, everyone has, been doing an excellent job on the things that can be reduced to pure functions. I think that the things that allow us to do things are sort of more of an open question. And, I don't have the answers, but I think that is where the real meat of Clojure's overall, ability to be a successful language is.
You're distilling libraries once you've already chosen, but often the first order of distillation is picking which library to.
Yeah.
Do you have any advice as to that?
be willing to throw away first attempts with the library. I mean, if there was some way to automatically say, yes, this will work, then, I would be the first to sign up. I have... I don't know if you saw Chaz's talk, but he talks about it a little bit. Like, there is a little bit of a sixth sense that you get for whether or not something will be amenable to this. But again, like, the more you get out of sort of Clojure's comfort zone, the harder it is to tell, and the harder it is to do this, because you have to understand the API deeply enough to understand how it's meant to be used. And so once you get to that point and you're like, oh no, this is crap, this will never work, now you've just filled your brain with something that will never work. And that's just the price you pay, right? You want to solve this problem badly enough so you are willing to kind of fall flat in your face a couple times. I'm sorry, there are two people, but the guy behind the back, he raised first.
So going back to the example before doing the protocols, you mentioned that one was not tested. I wonder if you could elaborate a little bit more what made that example.
Sure. So the artifact of all of our computation at the end of that is a single function, right? We take all these complex things, and we have functions calling functions, but at the end of the day, all we're handed is something that we can invoke, right? And invocation is, in this case at least, a side effect, right? It does something, and the only way that we can be assured that it's doing the right thing is to invoke it, let it draw something, and then see if it's right. There's no more introspection we could do. There is potentially the ability to layer metadata on top of this and to effectively bring that along, but that doesn't give us anything that the final solution. Wow, that's a bad choice of term. The last way of doing this is, it's kind of like the second and a half step, and we might as well just go all the way at that point. Yeah.
So I've never done worked much with Java libraries, let alone wrapping them with Clojure or any other language for that matter. But I need to do something like this for a project of mine, and I'd like to be able to share it with people.
Mm-hmm.
At what point do you decide when to stop and just with what the thing that's going to work perfectly for my project, I can keep going and implement more than API and all that stuff. When do you stop?
Well, first of all, give up on perfect. It's like it's good enough, and it's always good enough. And if you do it like Dave did Seesaw, then you have an escape hatch. So if everything works perfectly, but there's one thing that you can't quite figure out how to do it, then you just call straight into it, and that's fine. But again, this is the same thing as picking a library. It's something you get a feel for, and this is why you need to use what you write for something, and you need to understand whether or not it's actually helping you. And so please don't ever wrap a Java library, put it out there, and then never touch it again, because if you're not actively banging on it and seeing what falls out, then it's not a useful library, right? It's an unproven, it's a notion of what a library could be that does this. Yeah.
So just as a slight response to that, there's nothing wrong with subset. So if you have a particular use case and you have a good abstraction that you can provide for a half or a third that is functional and accessible and usable and particularly idiomatic with regard to all the things you like about Clojure, that's a perfectly fine thing to put out there, especially if you run into that end case where you're like, oh, this part of the library is just junk. I'm never going to be able to bring this over properly, but this other part is okay.
Right. Just going back, like I said, if you have a Swiss Army knife and all you need is a bottle opener, cool, don't do that, right? But, be cognizant of the fact that, your perfect working set is a moving target. And so, this is something that you need to just, understand that, there may be some scope creep as you start to do this, as you start to really understand how this library can be useful. So, Chaz is completely right, but don't hold on to, your assumptions for too long. Is that it? Oh.
When you work with Clojure, you work with maps, and when you work with Java, you work with Java objects that have getters and setters and so forth. One of the things that I come across is that there are some libraries out there that will sort of automatically make a Java object with getters and setters out of the maps, but that doesn't seem to be a central way of doing things in Clojure. Is there?
I'm sorry, you're talking about taking a map and turning it into a Java object?
Taking a map, let's say you got a map of properties, then you have a Java object and you have to change those properties with getters and setters, and you often find that you're writing getters and setters for each property. You want to do that just sort of automatically.
I mean, there's no...
Not to do that? I mean, why is it not as frequent as you would expect it to be out there?
I mean, I don't know, like, you know, often things with getters and setters, I mean, unless it's a sort of the big ball of mud where, like, the data and the actions and everything are kind of mixed together, but, like, a lot of code is taking maps and doing a set or something like that. And, you know, one approach you can use for this is that you can actually have a map of keys onto functions that accept an object and a value and, like, do that. And then, you know, you have that sort of implicit mapping on both of these things. But, I mean, it's hard to come up with a general solution that doesn't require a lot of reflection on the object and is only sort of guaranteed to mostly be right and all this other sort of stuff. And, I mean, this is code that you write once. And, like, if your understanding of the Java API is correct, then it works, and you can put that away in some sort of namespace and be done with it. And so, like, this is a necessary task in most cases, but I'm not sure that this is something that can be abstracted away necessarily.
Just to follow up on it, there is, I think, a closure function like bean or something like that.
Yeah. So bean will do that as long as it follows the Java bean, like, you know, and like with all the caveats there, and it comes out camel cased, and like, you know, I'm kind of contradicting myself saying that camel case is not a code smell, but like it typically you don't expect to see that in a normal like Clojure hash map, and so it like that gets you part of the way, and like you certainly shouldn't like shy away from that if that really just, you know, solves the problem for you, but it's not a panacea, right? I actually, do we have even? Oh, well, there we go. Yeah, we still have time for questions, I guess, if anybody has one, but if not. Well, thank you.